Today I will be discussing Lab 1 looking at constant velocity motion. In Lab 1 we were tasked with going out into the world and finding some object that moves at a constant velocity. This constant velocity can be determined using Newton's second law, which states that an object in motion tends to stay in motion and an object at rest tends to stay at rest unless acted on by outside forces. In this video I will first look at Newton's second law. Then I will analyze the motion of my object in Tracker. Next, I will use the data obtained from Tracker to create a computational model using VPython. Finally, I will compare my experimental data with the computational model to look at my object's motion. The most common form of Newton's second law is shown in this equation. It states that final velocity equals initial velocity plus the net force divided by the mass of the object times change in time. Another formula we will be using is the position equation, which states that final position equals initial position plus velocity times change in time. Looking at Newton's second law, we can see that an object with a net force of 0 would cancel out this whole side of the equation, making it final velocity equals initial velocity. This means that if the net force is 0, then there is no change in velocity. Now I'm going to analyze the motion of my ball in Tracker. Looking at the video, you can see that the ball moves at a constant velocity in the negative x direction. When choosing the axis orientation, I put the origin of the axis on the ball. This means that the ball is moving from the origin at 0, 0, 0. My choice of the orientation of the axis was simply a preference. If I wanted, I could have made it so that the ball moves in a positive x direction, like so. This would mean that the data is simply switched to go to the positive x instead of the negative. Using Tracker, I was able to identify this time step in between each frame and the change in position for each frame. This data will be useful in determining what the model will look like. This is the code that I used to create the computational model. First, I had to set initial conditions. The ball's mass is set at 0.476 kilograms. The initial position of the ball is set at the vector 0, 0, 0, which is the origin. The time is also set at 0. Initial velocity is set at the vector negative 0.027 in the x direction. This is for every time step, or delta t. Delta t is the frame rate of the video that I took, which is at 1/30th of a second. This is the calculation loop of my code. You can see that while time is less than 1 second, this loop will run to determine the position of the ball. The net force acting on the ball is equal to the vector 0, 0, 0, which means there is no net force. Using Newton's second law, we can see that the ball's final velocity is equal to the ball's initial velocity, since no net force cancels this side of the equation. The ball's position is equal to the ball's initial position plus the vector negative 0.027, which is the velocity. If I run my code, you can see that the ball moves in a constant velocity in the negative x direction. If I look at the graph, you can see that the position is plotted through 1 second. By creating a spreadsheet and plotting both the computational model data and the experimental data onto one position versus time graph, we are able to see that the experimental data does not exactly line up with the model. This is due to the nature of the motion of the experiment. Although the computational model assumes that the net force acting on the ball is equal to 0, we know this is probably not true. There are many different forces acting on the ball, too many to account for, but we will look at the main ones: friction, wind resistance, and gravity. Although gravity is usually cancelled out by the opposing force of the ground, if the floor was not exactly level, then gravity could have increased or decreased the speed. In conclusion, the motion of the ball is found to have not been exactly constant velocity. This is due to the small discrepancy in the experimental data and computational model. The model can still be used to determine the exact location of the ball if it is moving at constant velocity.